$284.3 billion.
Wow.
That was the revenue of the U.S. online ad industry in fiscal year 2021.
It's a number that's
No.
it's just really hard to wrap your head around. It's like the GDP of a whole country, like Portugal.
Exactly. And for this deep dive, we want to look at the engine that actually generates that value.
Right, because it's not just about putting a banner on a website. The real heavy lifting, the computational magic, is in deciding which ad you see.
Which brings us to our topic, click-through rate prediction, CTR. And specifically, we're tearing down a paper from researchers at Meta.
It's called DHE, a Deep and Hierarchical Ensemble Network. And, despite the very academic title, it's actually a pretty dramatic story.
Dramatic how?
Well, it's a story about hitting a wall. For years, the rule in deep learning was just go deeper, stack more layers.
Like deeper is better, more layers, more intelligence.
Right, but in CTR, that just stopped working. They found that adding more of the same kind of layer, it actually made the models worse.
That just feels completely wrong.
Yeah.
Counterintuitive.
It is. They called it the homogeneous trap. And their solution, this DHEN model, basically says you don't need a bigger brain. You need a more conflicted one. A team of rivals.
A team of rivals. I like that.
And on top of that, they had to build a whole new engineering hack just to make the thing train without, melting the servers.
Okay, so let's set the stage. Why is this so hard? I mean, CTR prediction, if I search for dog food, show me an ad for dog toys. Seems simple enough.
If only. The real problem is something called feature interaction. That's the key concept.
Okay, break that down for us.
So feature interaction is when one piece of data changes the importance of another. The classic example is diapers and beer.
Ah, the data science legend.
Right. On their own, they have nothing to do with each other. But data show that on Friday nights, young fathers would often buy both together.
So the feature time of day changes the relationship between the feature's user demographics and product category.
Exactly. It's a complex, high-order interaction. And in the old days, with logistic regression, a human had to literally sit there and guess those rules.
Which is just impossible at scale. You can't write an if-then statement for billions of people and products.
No way. And that's why deep learning models like Wide and Deep and Deep FM took over. They automate finding those interactions.
So what went wrong? If deep learning was the solution, why did they hit this wall?
It's that homogeneous trap again. The industry kind of got stuck in a rut. The thinking was, okay, this interaction module works. Let's just stack 10 of them.
It's like my guitar amp. It goes to 11.
And it sounds terrible. The paper points out that stacking identical layers just amplifies the errors and blind spots of that first layer.
Yeah.
It doesn't add new perspective. It just adds noise.
So diversity was the answer.
That was their hypothesis.
Yeah.
The different kinds of neural networks see the world differently. They capture non-overlapping information.
Okay, so let's get into the anatomy of DHEN. Deep Hierarchical Ensemble Network. I'm guessing ensemble is the key.
It is. They basically built a single layer that's like a container. And inside, they put a bunch of different experts.
A team of rivals.
Exactly. First, you've got the veteran, advanced DLRM. That's the industry standard model that was already running at Meta.
So the baseline.
Right. Then they throw in self-attention. This is the architecture from Transformers, from ChatGPT. It's brilliant at finding long-range context in data.
The language brain.
Then you get convolution modules. We usually see those in like computer vision for images.
Or pixels.
Yeah, for pixels. But here, they use them to find local patterns, like features that are next to each other in the data.
So a vision brain and a language brain are both looking at my user data.
And a math brain, too.
Yeah.
They add deep cross nets, or DCNs, which are designed to explicitly find certain kinds of mathematical interactions, and simple linear layers to just condense information.
It sounds chaotic, all these different things running at once.
It is, but it's organized chaos.
Yeah.
And that's the hierarchical part. They stack these mixed layers.
So the output from the self-attention in layer 1 gets mixed with the output from the convolution.
And that mix becomes the input for all the experts in layer 2.
Yes.
The model starts to learn the interactions between the different architectures. It's a whole new level of complexity.
Did they find any specific combinations that worked really well?
They did. This is a really cool insight from the paper. The combo of self-attention and a simple linear layer was a huge winner.
Why those two? One is super complex, one is basic.
Well, self-attention is incredibly powerful, but it's also famously unstable and hard to train. The researchers found that putting a simple linear layer next to it sort of stabilized it. It pre-processes the data in a way that helps the attention mechanism find the signal faster.
So the boring, reliable layer helps the fancy, creative one do its job.
It's a perfect example of why the diversity works. They cover each other's weaknesses.
That makes a ton of sense. But I want to pivot now to the engineering side of this, because you can design the world's greatest model, but you still have to run it.
And this is where the paper gets into some really hardcore systems challenges.
They use this phrase that I just love. They call the model embarrassingly sized.
It's a great term, isn't it? Embarrassingly massive.
What makes it so big? It's not just the depth, the number of layers, is it?
No, it's the width. It's something called embedding tables. This is crucial for recommendation systems. You have two kinds of data features, right? Dense and sparse.
Dense is just numbers, like my age or the price of a product.
Right, easy for a computer. But sparse features are things like my user ID or a video ID. They're categories. You can't multiply John Smith by a number.
So you have to translate John Smith into numbers first.
Exactly. The system gives him a unique vector of numbers. It's embedding. And you store these vectors in a giant lookup table. So if you have, say, a billion users.
You have a table with a billion rows, and that's just for users.
And then you have tables for products, for ads, for pages. These tables are terrifyingly large. Terabytes. The total parameters can be in the trillions.
And a top-of-the-line GPU, like an NVIDIA A100, only have, what, 80 gigs of memory?
Yep. So the model doesn't fit on one chip. It doesn't even fit in one server. It's just embarrassingly large.
So how on earth do you train it?
Well, the normal approach is data parallelism. You just copy the whole model onto every GPU. But you can't, because it doesn't fit.
So that's out.
So the next step was something called FSDP, fully sharded data parallel.
Sharded as in chopped into pieces.
Exactly. You take that massive embedding table and you chop it into little shards. You put one piece on GPU 1, another on GPU 2, all the way up to, say, GPU 128.
Okay, so now the model fits in memory. Problem solved.
Not quite. New problem created. Because for the model to work, the GPUs now have to talk to each other constantly to get the pieces they need.
A communication bottleneck.
It's an operation called all gather. It's brutal. It's like, imagine 128 people in a room, and every single time one person makes a move, they have to shout and get an update from the other 127.
You spend all your time shouting, not working.
And it gets worse. The paper highlights the physical reality of the hardware. They used a system called Zionites.
Oh.
Think of a server rack. Inside one physical box, you have 8 GPUs connected by this super fast interconnect called NVLink. It's like 600 gigabytes a second.
So those 8 GPUs are sitting at the same table. They can talk really fast.
Right, but the whole system has 16 of these boxes. And to talk between the boxes, you use the regular network called RoCE. And that's maybe 25 gigabytes a second.
Whoa. So it's more than 20 times slower to talk to the box next door than to your immediate neighbor.
24 times slower. And the old system, FSDP, it didn't care. It treated all 128 GPUs as one big, flat group. It was constantly trying to shove massive amounts of data across those slow network links.
The software didn't understand the hardware's geography.
Perfectly put. So the Meta team built HSDP, Hybrid Sharded Data Parallel.
And how does the hybrid approach work?
It respects the box. HSDP only shards the model among the 8 GPUs inside a single host.
So all that heavy sharding traffic stays on the super-fast NVLink.
Yes. Those 8 GPUs essentially act as one giant super GPU. Then between the different boxes, it switches back to the old method, data parallelism.
Ah, so you get the memory savings of sharding, but you keep the communication local and fast. You only send the smaller updates across the slow network.
That's it. It's an elegant solution that matches the software strategy to the physical hardware topology.
And what was the result? Did it work?
It worked great. They got up to a 1.2x improvement in training speed. But more importantly, it allowed them to train these huge DHEN models at all. The old way would have just ground to a halt.
It's such a great example of co-design. The algorithm and the system have to evolve together.
You can't separate them at this scale.
Okay, so they built this incredible, diverse model, and they built a custom training system to run it. Let's get to the payoff. Does it actually predict clicks better?
It does. They measure performance with a metric called normalized entropy, or NE. Lower is better.
And the final score was?
The DHEN model achieved a 0.27% improvement in NE over the old state-of-the-art model.
Okay, I have to be the skeptic here. I can hear people listening and thinking, you just spent 10 minutes talking about hardware and heterogeneous layers for 0.27%. It sounds tiny.
I was waiting for that. And you're right. In almost any other domain, that's a rounding error. But you have to go back to the number we started with.
The 284 billion.
Exactly. When you are serving literally billions of predictions a day, a 0.01% improvement is a huge deal. A 0.27% improvement, that is massive. It can translate to tens of millions of dollars in revenue and efficiency.
It's the law of large numbers. A tiny edge, a billion times, is a huge advantage.
It's the difference between a good quarter and a great one. But honestly, there's a result in the paper I find even more compelling than the raw number.
What's that?
It's about how the model scales. They compared DHEN to another popular approach called mixture of experts, or MOE,
Right.
and they found DHEN was just more efficient. It got better results for the same amount of computation. But the real mic drop moment came when they started feeding it more data.
How much more?
They tested it on data sets, from 5 billion examples all the way up to 35 billion examples.
35 billion. The scale is just dizzying.
It is. And they found that the performance gap between DHEN and the baseline model got wider as the dataset got bigger.
Wait, really? Usually models hit a point of diminishing returns. They plateau.
They do. But this suggests that DHEN didn't. That diverse hierarchical structure wasn't just memorizing the data, it was actually learning more general, more powerful patterns from it. The more you fed it, the smarter it got, and the further it pulled ahead.
So, to pull this all together, we started with this homogeneous trap. Stacking the same thing over and over was a dead end.
An echo chamber, yeah. And the solution was diversity. Mixing these different architectures from vision, from language, so they could cover each other's blind spots.
And the whole thing was enabled by a smarter training system, HSDP, that understood the physical layout of the computers it was running on.
You need the right team, and you need the right stadium for them to play in.
There's a bigger idea here I want to end on, kind of a philosophical point about artificial general intelligence, or AGI.
The dream of a machine that can truly think.
Right. And a lot of the current work, with the big LLMs, it's basically just scaling up one massive homogeneous architecture, just more and more transformer layers.
It's the deeper is better philosophy, just taken to the extreme.
But this paper kind of suggests that for messy, complex, human-scale problems, that might not be the most efficient path forward.
It's a really provocative thought. I mean, the human brain isn't a uniform block of gray matter, right? We have a visual cortex, an auditory cortex, a prefrontal cortex. It's an ensemble of specialized modules.
We are a hierarchical ensemble.
We are. And this paper proves, at least for this one very valuable problem, that a team of specialists beats one giant generalist. So maybe the path to AGI isn't building one perfect universal algorithm.
But what?
Maybe it's building a society of thousands of different specialized narrow AIs, all communicating, all checking each other, and all learning from the interactions between them.
The society of mind.
Exactly. And if DHEN is any guide, that society needs to be very diverse to actually work.
A fascinating thought to end on. Well, that wraps up our deep dive. Whether you're building models or just building a team, remember that sometimes a little bit of healthy conflict, a little diversity, is exactly what you need.
Couldn't agree more.
Thanks for listening. We'll see you on the next one.